Welcome back everyone to our calc series. Today we are going to talk about selecting procedures for derivatives and higher order derivatives. So 3.5 is all about selecting procedures and 3.6 is all about higher order derivatives. And the one that's actually useful or like has new stuff is 3.6. 3.5 is all about knowing which one to choose, and this sense really comes from doing a lot of problems, which we'll do in our problem sessions. But um, so we're going to take this chance to just review all the different ways of calculating a derivative. So this is what selecting procedures is going to be all about. And before I go through any of these or review any of these, I would just like to note that often derivatives come with a combination of these rules. Often sometimes you have to do many layers or many chain rules, especially. And so it's not all about just one rule, but I'm just going through all of these for review. So product and quotient is whenever you have two expressions multiplied or divided by each other. So here, for example, we have a product. So the derivative of this, we're just going to do quickly, is the derivative of the first times the second plus the derivative of the second times the, the first. So like this. Then for quotient, you would just use the quotient rule, right? So this would be derivative of the numerator times the denominator minus the derivative of the denominator times the numerator. And you would take that over the denominator squared. So I'm not going to simplify this anymore. Okay, then we have the chain rule. So whenever you have composite functions, this is arguably the most useful rule. So here, for example, you have these chained together. And over time, again, you should try to get yourself uh, completely accustomed to to using the chain rule so that you can do it more quickly and automatically. So usually what I do is I consider what's outside. I would take the derivative of this with respect to what's inside. So I would just go cosine, oops, cosine e to the x, and then I would consider taking the derivative of what's in here. And then for this one, it's the exact same. It would just be like this, right? And I'm going to take this chance to do one that has multiple layers. So let's say we had sine e to the sine e to the x, like this. So then here we have essentially four layers, but I'm going to show you how I can still do it with the chain rule, like using just intuitively, right? Because what you could do is you could define like four layers, but so with intuition, what you could do is you would go like, okay, well, I want the derivative of sine of, let's first take this part, right? So the derivative of this sine expression with respect to this big chunk. So that's going to be cosine of this big chunk. Then I'm going to consider taking the derivative. This needs to be multiplied by the derivative of this thing. So then I'm going to consider the derivative of this, and then I'm going to set this part as the new big chunk. So this is, or actually let's call this the medium chunk. Then this we can write as, so this would just be e to the sine ex, like this. And then we want to take the derivative of this chunk. So this smaller, and then we can define an even smaller chunk, which is this e to the x. So this should be multiplied by the derivative of this sine e to the x, and that would be cosine e to the x times the derivative of e to the x. So that's just going to be e to the x, like this. So that is how you can sort of like peel apart the function like an onion, and you would just gradually go inside. So you start big and then you gradually peel in. So this is like one way you can intuitively do the chain rule. Okay, then we have implicit differentiation. So one classic example is just this Pythagorean theorem-ish thing. So whenever you have something like this, um, or like D, then you can just implicitly differentiate. So these are some techniques. And overall, again, it's all about a combination of these rules. And we're going to do some practice sessions about differentiation. We're just going to do a lot of differentiation. And here, we have some further examples. So here we go. This first one is clearly you would first want to do a product rule. So it's like the derivative of this times this, and then plus the derivative of this times this, right? So the derivative of this first part then would require a chain rule. So that would be this times 1 over x times e to the x plus you would take the derivative of e to the x times this first factor itself. Do I need another one? Yes, I do. Okay. And then later you could also choose to organize this or like take some common factors like this. Okay. Yeah. Here, this is clearly implicit, so you would just do something that we've done so many times for then dy over dx is equal to 1 minus y x minus 1. For this one, again, it's implicit, but then it would require, again, some other rules. It's a combination of multiple rules. You would take the derivative of both sides with respect to x. So notice here how there were actually 3 layers, and I just did it intuitively using the method I just showed. And on the right-hand side, we would have negative sine x. Then you can just organize this. Dy over dx is equal to negative sine x times y over cosine ln y. Okay, then we get to the actually useful part. Again, selecting, not saying that any of this is not useful, but like selecting procedures is more about just the feeling, right? So I just went through a brief review. Okay, so higher order derivatives are basically, the idea of this is just you take the derivative of the derivative of the derivative of the derivative of a function. So if you have a second order derivative, you take the derivative of f twice. So you would go, for example, if we had f of x is equal to ln x, then this is the normal derivative, right? You take it once. Then you could take it twice, and that is what we call the second order derivative. So, oops. It's what we call the second order derivative. Then you can take it again, and this would, oops, 2 over x cubed. This would become the third order derivative. So the idea of this is that you just keep treating this the derivative that you just got as a new function, and you take the derivative of that. So when you get from d like the nth derivative to the n plus 1 derivative, this is the idea. You just consider this as a new function, and you take the derivative of that. So in general, the notation here that I've just used, this is the Leibniz one, and it's d n y over dx n. I'd say in general, this is pretty easy to master intuitively. So we're just gonna do some examples here. Oh, well, I just did this first one, right? These are the first 3 derivatives. Next we have the 3 derivatives of this. And presumably we want dy over dx, we want d squared y over dx squared, and d3y dx cubed. So the idea for this is that we can do implicit, and we can express each of these in terms of x and y. So let's see what happens. So we take the derivative of both sides with respect to x. That would be 2x plus 2y dy over dx is equal to 0. So dy over dx is just equal to negative x over y. Okay, so that is our first derivative, and this works. Then we want to find the second derivative. And what we're going to do is we're going to treat this as our new function, and we're going to consider, actually, let me write this a little bit more completely. D squared y dx squared is equal to d over dx of x over y, which is like this new, or like if I want to write it even more completely, it's just dy over dx. And that would be d over dx of x, negative x over y. And also, if you look at this carefully, then you would see why it is written like this in Leibniz notation. If you just do some more observation. Then this we could use a quotient rule. This would be equal to negative of y minus dy over dx times x over y squared. And dy over dx is just this, so we would plug this in again, and this would be y minus x plus x squared over y squared, and that would become negative y squared minus x squared over y squared, over y cubed. And actually, we would find that since x squared plus y squared is 1, then this will just be negative 1 over y cubed. Okay, so this is our d squared y over dx squared, right? And then we would go on to do d cubed y dx cubed. So this is just the derivative of the second derivative, and that would become d over dx of negative 1 over y cubed. And this, by the power rule, would be 3 times y to the negative 4 times dy over dx. And dy over dx is just this. So it would be 3 times 1 over y to the 4 times negative x over y, and that is negative 3x over 5y. So we have expressed all the higher orders in terms of x and y. And as you can see, this was some tough work, and this is one of the harder questions, I would say, for the AP. Okay, and it doesn't appear on the AP itself, right? So this is just like a random example question. Then if f of x is x to the 99, we want to find the 99th and 100th derivatives. So what we're going to do is we're going to look at some lower order examples, and hopefully we can find some patterns. So we have f of x is equal to x to the 99th. Then f prime of x would just be 99x to the 98. And f prime prime x is, or like the second derivative, is equal to 99 times 98x to the 97. So it seems that of course this exponent would be decreasing one at a time, and the coefficient seems to be sort of stacking up the exponents that were once there. So like this, it's sort of like a record of the exponents. So by the time we get to f to the 99, we should have 99 numbers. So like for this third derivative, we have these 3 numbers, right? For this first derivative, we have 1. So this should be equal to 99 numbers, and according to this pattern, this should be 99 times 98 times 97 all the way until times 1. So then this is perfectly 99 numbers. And x's exponent should be x to the 99 minus, so here every time we take off 1, and we've done this for 99 times, so that's x to the 99 minus 99. And that would become, this would become 0, or it would become 1. Sorry, this is x to the 0, so this is 1. And this we can write as 99 factorial. Factorial means basically, n factorial means you multiply from n all the way to 1. In general, this is for integers. Of course, there are people who've expanded this to negatives and decimals and real numbers. So f prime 99 is just 99 factorial, right? Okay, so then f prime, or like the 100th order derivative, would be what? Well, this is already a constant, right? And if we take the derivative of this, so again, we treat this as a function, and we take the derivative of this with respect to x, the derivative of a constant would then be 0. So this is it for today's video, and we'll be doing a practice session where at least one practice session where we'll be practicing a lot of derivatives. Thank you.